Section 7.4, evaluate logarithms and graph logarithmic functions. Let's see what the next slide is. What is a logarithm? All right, so this is a video from, actually, my high school math teacher. And if you take pre-calculus with me, you will also have him as a teacher because we recorded a bunch of videos together, and we kind of co-teach pre-calculus. This teacher from St. Louis, and this is his lesson on logarithms. Don't worry about taking notes right now. I will tweet out the lesson later if you want to watch it again. But just kind of sit back and listen and try and learn as much as you can from the video. It's about 3.5 minutes. Here we go.
How is the difference between .0000000000398 and .00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power of p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked.
Okay, so this is the definition of logarithm. Rewrite some stuff using the definition of a logarithm. All right. Well, we just learned the definition. In your book, these will be phrased as write in exponential form. Okay, so if we wanted to write these in exponential form, here's what we're going to do. Remember that the base is the same for the logarithm and the exponent. So we'll take the base raised to a power equals the number. Well, remember in Mr. Kelly's little video there, this was p, that was the power, and 8 was n, that was the number. So we would take 2 raised to the 3 equals the number, which was 8.
0 power.
Yeah, 4 raised to the 0 power equals the number, which was 1. Does 4 to the 0 equal 1? Yeah, I think it does. You can check your calculator. That's actually a true statement. Okay, so there's 2 ways that we could write this. The next one, we're going to do the same way. I'm going to take 1/4, that's my base, raised to the power, which was -1, equals the number, which was 4. Is 1/4 to the -1 4? Yeah, I think it is, right? You can check it in your calculator. We have that rule that if we take a fraction of the negative number, we just flip it. All right, well, log base 4 of 64 is really asking you to figure out what it equals, but it's really asking this. 4 raised to what power equals the number? Equals 64. Well, let's check. 4 to the 1 equals 4. 4 squared equals 16. 4 cubed, what is 4 cubed? 64. So the log base 4 of 64, we just figured out, was 3. 4 raised to the third power equals 64. Please correct the typo. It is log base 5 of 0.2 is what it should say. 0.2. I know, I'm sorry. 0.20. So it should be, in fact, I'll just rewrite the whole thing for you. Log base 5 of 0.20 equals what?
You have to add the 0 after the 2.
You don't, no. So, this is really asking me 5 raised to what power equals 0.2. Now, these are kind of tricky when they're in decimal form. So let's put 0.2 into a fraction. 5 raised to what number equals, I think 0.2, isn't that 1/5? Or 2/10, which reduces to 1/5. So the question is, 5 raised to what power gives me 1/5? Well, if I have a fraction, I better be thinking negative powers, right? So if I take 5 raised to the, we'll start with 1, -1, that equals, well, that rule that says something raised to the negative power flips it, tells me that 5 to the -1 is 1/5. Oh, look. I think I just won. Okay, so log base 5 of 0.2 is -1. All right, so just to kind of point out what my answer is here. Negative 1 is the solution to log base 5 of 0.2. Log base 1/5 of 125. All right, so I want to know what that is. So really, this is asking us 1/5 raised to what power equals 125? Oh, yikes.
Did you do this on a calculator?
Yes and no.
So, yes.
When we're dealing with fractions, we should be thinking about negative powers. All right, so let's check. 1/5 raised to the negative 1. What does that equal? 5, right? That just means we flip the fraction. 1/5 raised to the negative 2. What does that equal?
Negative 25. Or 25.
25, right? It's 1 over 25, but then flip that, so it's 25. What is 1/5 to the negative third? Sorry, I'm running out of space here. 1/5 to the negative third. You could try that in your calculator, and I think it would spit back 125. So what is my solution then? I checked. Yes, negative 3, right? I checked negative 1, that was wrong. Negative 2, that was wrong. Negative 3, however, that one worked. All right, so my solution is negative 3. 1/5 raised to the negative third power is 125. Log base 27 of 3 is really asking us 27 raised to what power equals 3? All right. What'd you say? 1/3. Yeah, that's good. 27 raised to the 1/3 equals 3. So our powers could be fractions. Right? 27 to the 1/3 power gives me 3. That means the cubed root of 27 is 3. So the solution to log base 27 of 3 is 1/3. Common logarithms. This is the logarithm that Mr. Kelly talked about. A common logarithm is a log base 10 of some number. And log base 10 is so common that they decided that, you know what, when we are talking about log base 10, we'll all agree to not write the 10. All right, so log base 10 of x just means, or is written log of x. It's very similar to when we write the square root of x. Well, we know that that's actually the square root, and we could write the 2 right there, but we never write the 2. It's just a similar idea. Log base 10 of x is just the log of x, also known as a common logarithm. And you have a button on your calculator for that. Later, the log button and then 8. What do you get?
0.903.
0.903? Okay, and now we could check our answer, right? Because if this is a common log, then there's actually a base 10 right here. And based on the definition of a logarithm, we should get 10 to the 0.903 equals what?
8.
It better be 8. Check. Does it?
0.903.
In science a lot also. The natural logarithm is the log base e of some number. So yesterday we said, hey, e is called the natural base. This is called the natural logarithm. And we shorten this. We just write simply the natural log of x as ln of x. Okay, so if you ever see ln of x, that means log base e of x. What is the natural log of 0.3? Negative what? 1.20. Give me another one. 4. Take the log base b of b raised to the x. What happens is the log base b and the b in the exponential cancel each other out, and I'm left with just x. I'll rewrite the other one here for you too. It says this: b raised to the log base b of x equals x. For the same reason, the exponential and the log base b cancel each other out, and I'm left with just x. 10 to the log of 4. All right, well, we know that if it's a common log, or we didn't write any base, that the base is assumed to be 10, right?
Yeah.
So if I take 10 raised to the log base 10, all that stuff cancels out, and I'm left with just 4. Because it's going to make some of the examples in your homework a little bit easier. It says this: if I have the log base b of m to the n, I can take this n and put it out in front of the logarithm. And then I just have to worry about evaluating this logarithm log of b base m, whatever that part is. You'll see why that's helpful in the example here. In this example, log base 5 of 25 to the x is I'm going to kick that x out in front of the logarithm. Okay, so this is x times log base 5 of 25. And if it says simplify, now the nice thing is I'm not worried about the x. I can't simplify the x anymore. But log base 5 of 25, I know how to evaluate that. I can turn that into some nice little number, hopefully. And remember that log base 5 of 25 is asking me, what is, or 5 raised to what power equals 25?
2.
Yeah, 5 raised to the second power, right? So log base 5 of 25 is actually 2. So I'm going to substitute 2 in for log base 5 of 25. So I get 2 times x. Here we go. So the first thing I'm going to do in this first problem is switch x and y. X equals 6 raised to the y. In fact, I'm going to give myself some more space here. 6 raised to the y. And then I'm going to take, the problem here is I have y in the exponent, right? I don't want it in the exponent. I want it by itself. So there's two ways we can think about this. We can think about this as using the definition of logarithms, or the way that I like to think about it is, I think, a little bit more natural for you guys is this handy little trick. If I take the log base 6 of the right-hand side, I also have to take the log base 6 of the left-hand side. All right? But notice, on the right, over here, the log base 6 of 6 cancels all that stuff out. And I'm left with just what?
Why?
Y. Because I said so. So on the left, I have log base 6 of x. So y equals log base 6 of x. That's the inverse of the original function. The other one. First thing I'm going to do in this one is switch x and y. Let's get that out of the way first. X equals the natural log of y plus 3. Okay, now the problem here is that I've got that y stuck inside of the natural logarithm. Remember, if we have the natural log, that's the same as the log base e of y plus 3, right?
Yep.
Okay. Now, how do I undo a logarithm? Well, I have to turn it into an exponential. On the left-hand example, I took the log base 6 because the base in the exponent was 6, or the exponential was 6. Here, I've got the log base e, so I'm not going to take the log of both sides, but I will take both sides and raise them with a base e. So on the left, I get e raised to the x, and on the right, that stuff all goes away, and I'm left with y plus 3. And then the last step is to subtract 3 from both sides. So I'm running out of room. I'm going to go over here to the right, and this is e to the x minus 3 equals y. Try these out for size. 503, 46, 9 to 15, 20 to 22, 30 to 33, 37, and 38. There is no graphing, you'll be happy to know.